So when we are considering the average total value of power, we can say that this particular quantity, that is cos 2 omega t plus phi, this term actually averages out to 0. So it will just represent the phase angle difference. Is it going in this particular direction? Is it going in that particular direction? That is what the negative sign indicates. The average power will be equal to I RMS into V RMS into cos phi. That is a general consideration. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we were dealing with alternating current. Today we have to solve some mathematical problems because we are going to identify what is the power in a series LCR circuit. It is going to be completely max, not much of a physical aspect to it, but let's see what happens. What are the interesting things we can see from this? So generally we do know that power can be expressed in of course, when we are speaking about current and voltages, power can be expressed in terms of the product of voltage and current, or simply in other words, we can say that it is I square R when we are expressing it in terms of resistance also. So generally we can say that P will be equal to VI or simply I square R. Now, since we are dealing with a series LCR circuit, resistance is also already included in the LCR. So we'll just take the equation, that is P is equal to VI, the general equation that is applicable to a DC circuit. I'm taking that particular equation. If I apply that to a series LCR circuit, what will happen to that circuit? Again, I cannot take the average values of voltage and current because they will cancel out each other. So what I'm going to take is the instantaneous values. So we already have an equation for the wave function that voltage and current produces in a series LCR circuit. That is, V will be written down as, yes, V naught sine omega t, and I will be written down as I naught sine omega t. But this was the general representation. But since we saw that, since in an inductive circuit or in a capacitive circuit, current seem to lag or lead to voltage, we'll have to account for that particular error. So let's say current has a probability of leading or lagging by a phase angle of phi. It can be pi by 2, it can be pi, I don't know. So generally I'm going to say current has a tendency to lead or lag. So I'm going to introduce this particular phase angle difference. In a resistive circuit, in a purely resistive circuit, phi will be equal to 0. In a capacitive or inductive circuit, it can lead or lag behind 90 degrees. So just to account for that, I'm just going to put a plus phi here. Now what I'm going to do is that I'm going to find what is the power. So it's very simple. So I'm going to change this and write the whole equation like this. Now what I'm going to do is that since I have multiplied these two equations, I'm going to slightly rearrange it. So what I'm going to do is that I'm going to take V naught and I naught together and I'm going to write these particular terms together. That is sine omega t into sine omega t plus phi. So again, from this, the mathematics is going to start. Simply, you can see that it is some constant that is standing up outside into sine A plus, that is. So this resembles the equation, that is sine A into sine B. So we are going to introduce trigonometry into this particular equation because I have no other choice to explain this current and power. To explain power to you, I have to include trigonometry. So what is sine A into sine B? Sine A into sine B is equal to 1 by 2 is equal to 1 by 2 into cos A minus B minus cos A plus B. So it's very simple. Instead of sine A into sine B, that is sine omega t into sine omega t plus phi, I'm going to apply this particular trigonometric result, and then it's only simplification from that point onwards. So the only thing you can do to understand this particular equation is just to practice and understand trigonometry. So I can rewrite this particular equation as P is equal to V naught I naught into V naught I naught into half into, so I'm going to put it in a bracket. So half into cos A minus B. That means cos omega t minus omega t plus phi. So cos omega t minus omega t plus phi into minus cos omega t plus omega t plus phi. So I can write it like this. So cos omega t plus phi. So when I open these particular brackets, you can see that it is omega t minus omega t in one side and omega t plus omega t in the other side. So I can simply write these omegas will cancel each other out. Omega t and omega t will cancel each other out and only phi will be remaining, which means cos phi minus cos 2 omega t plus phi. So if I open the bracket, I can write V naught I naught into half into cos omega t minus omega t 0 minus phi minus cos 2 omega t plus phi. So I have this particular result. So what is negative cos phi? That is cos of negative phi is nothing but negative cos phi. So I can write, I'm going to take this half outside. So I can write this as V naught I naught divided by 2 into cos minus cos phi minus cos 2 omega t plus phi. That's it. So again, we'll arrive at this particular equation which will give us the actual instantaneous value or instantaneous value of power. So power will be equal to this particular quantity, but we are not taking the instantaneous value, that is at the every instant. We'll only be considering an average total value of power. So when we are considering the average total value of power, we can say that this particular quantity, that is cos 2 omega t plus phi, this term actually averages out to 0. So we can say that when we are taking the average value, this particular function will average out to 0. So this entire term will be avoided from the equation and only cos phi will be remaining. So when we are taking the average value, P average will be equal to the already existing V naught I naught divided by 2 into the only remaining quantity, that is cos phi. So we'll only be taking this much quantities. Now the final thing, the only thing we have to do in this particular case is that, so we'll consider splitting this denominator into 2. That is, this particular equation, again I can write it as V naught by root 2 into I naught divided by root 2. Right? If I split this particular equation, the denominator will become V naught by root 2 into I naught by root 2. That is V naught into I naught divided by root 2 into root 2. Root 2 into root 2 is nothing but 2. So I can write it like this, into cos phi. This cos phi just indicates that this cos phi is just there to represent the phase angle difference. Okay, so it will just represent the phase angle difference. Is it going in this particular direction? Is it going in that particular direction? That is what the negative sign indicates. So we don't have to consider the negative sign. So we'll just say that V naught by root 2 into I naught by root 2 is into cos phi will give us the average power. But again, we know one more equation. This is the last substitution, that V naught by root 2 or I naught by root 2 is actually the RMS values that we actually obtained in the previous classes. So I can actually write this particular equation as V naught will become VRMS, that is V naught by root 2 will become VRMS into I naught by root 2 will become IRMS into cos phi. So VRMS into IRMS into cos phi will be the final equation you can take to find what is the average power output in a series LCR circuit. So again, if you can apply this particular equation to any AC circuits and you'll get the average power output. We can apply this equation to a normal inductive circuit or a capacitive circuit or a purely resistive circuit, and we will still get what is the output, what is the net power output. So let's see, we can apply this to various circuits. Let's say for a purely resistive circuit. So for a purely resistive circuit, power, that is P average, will be equal to IRMS into VRMS into cos 0. Why? Because in a purely resistive circuit, that is in a circuit where there is only AC power source and a resistor connected like this, we saw that the voltage and current were both in phase with each other, which means the phase angle difference, that is the phase angle difference phi between voltage and current, is actually 0 degrees. So because of that particular reason, cos phi will become cos 0, and cos 0 is nothing but 1. So we can actually say that this will be equal to IRMS into VRMS. So in a purely resistive circuit, power will be equal to the product of the RMS value of current and the RMS value of voltage. You can directly multiply them and you will get maximum power output. But what about in the case of a purely capacitive or purely inductive circuit? So again, in a purely inductive or capacitive circuit, current seems to either lag or lead to voltage. There is a difference of 90 degrees. The phase angle difference between current and voltage is 90 degrees, which means phi will become 90 degrees. So I can actually say that in a purely capacitive circuit or purely inductive circuit, I can say that it will be equal to IRMS into VRMS into cos 90 degrees, right? Even if it is leading or lagging, it is by 90 degrees. So I can say that this will be equal to cos 90 degrees, which means the average power output of a purely inductive or capacitive circuit will be, it will be 0. It will be equal to 0 as cos 90 is nothing but 0. So since cos 90 is 0, then automatically the average power output will be 0. So that is why I said in the earlier classes that when we take the average value of certain circuits, for example, inductive circuit or a capacitive circuit, if we take the average value, then it will be 0. If I am taking the average value of power in a capacitive or inductive circuit, it will be 0 because the angle between current and voltage in that particular circuit is 90 degrees. Automatically, the average power output will be 0. That does not mean that the circuit is not having any power. It is not generating any power. It has power. It is generating power. But the problem is that if at one instant it is a peak value, then the next instant it is a low value. The next instant it will be a peak value. The next instant it will be a low value. So instantaneously there is power being produced, there is power output. But the problem is that when we take the average, that is, if I take this plus this plus this divided by this, it will be equal to 0. If I take the average, that is, one is positive, one is negative, one is positive, one is negative. If I take the average, this plus this, 0, this plus this, 0, divided by 2, again 0. So the problem is that when I take the average value, it will be 0. That is why we can't take the average value of certain quantities. I have already explained that. Just like that, I cannot take the average power output of a purely inductive or a capacitive circuit because the angle between current and voltage is actually 90 degrees. So hence we cannot take the average power output. So again, lastly, this type of power where in a purely inductive or capacitive circuit, when the average power is equal to 0, then those sort of circuits, I'm going to write it here, inductive or capacitive. And this one is purely resistive. It is purely a resistive circuit. This one is an inductive or capacitive circuit. So this type of current where the average power output is equal to 0, this type of current is also known as wattless current. This type of current is also known as wattless current. That is because the average power is equal to 0. That is why we call it as wattless current. It's very simple. So again, to summarize, the only thing we did was that we knew what was the equation for power, that is P is equal to VI or I square R. Since we are using current and voltage in this particular case, we took the equation P is equal to VI. We considered the instantaneous values of voltage and current. Now, since current might lead or lag behind voltage, we assumed that probability and took phi as a constant here. So it can be 0, it can be 90. So then again, we rewrote this particular equation as V naught I naught into sine omega t into sine omega t plus phi. So this resembled the trigonometric result sine A into sine B. So applying that particular result, we arrived at the conclusion that the average power will be equal to I RMS into V RMS into cos phi. That is a general consideration. Now if you apply that for a purely inductive or a purely resistive circuit, we knew that since the angle between the phase angle difference between voltage and current is 0, the average power output of a purely resistive circuit will be equal to VRMS into IRMS. Just like VI, we'll get VRMS into IRMS. So we'll get the average power just like in a DC circuit. But for an inductive or a capacitive circuit, the problem is that the average power will be equal to 0. That is because there is a phase angle difference between the voltage and current flowing through that particular circuit. That is 90 degree, hence we'll get 0. Those kind of powers are actually known as wattless power. So that is all about power in a series LCR circuit. Now we have to learn one small thing, that is resonance. So what exactly is resonance? You might have heard this term a million times in high school, or whenever you learn physics, that is acoustics and all that, you might have heard about resonance. So what exactly is resonance? So the interesting thing about resonance is that it is actually visible in our day-to-day lives, and it is sometimes creepy or jaw-dropping. So the point is that you might have seen that opera singers, that is the fat lady that sings. So opera singers, not calling opera singers fat, but that's a term. So when the opera singer sings at, let's say, a specific tune, let's say C sharp, like that, if they sing, the wine glass actually starts to vibrate and break. So when they starts to sing at a specific tune or specific pitch, then the wine glass actually start to vibrate and break. And there was actually an incident in London, that is during the World War time. A couple of German soldiers, not in London, some other place actually. So a couple of German soldiers were actually marching beyond a bridge. So there was a bridge like this, and here it was water. So they were marching across a bridge like this. So it just so happened that it was a very strong bridge made out of bricks. So when they marched across this particular bridge at a particular point in time, the bridge entirely collapsed. Nobody knew why. It was a perfectly good bridge. No problem was there. But suddenly the bridge entirely collapsed. So the only thing they could find out was that since the soldiers were marching across the bridge, at some point something did to that particular bridge. Because they were marching, something happened to that particular bridge. So they later figured out that, applying a little bit of physics, the marching of the soldiers, that is this particular marching, so it produced vibrations. This particular vibrations was equal to the natural vibration of that particular bridge. So you have already studied in first PUC and in high school that every object will have a natural frequency. Every object will have a natural frequency, a natural vibration state. So that particular vibration, when it is equal to the vibrations which we produce externally, then both of them will start to oscillate. meaning this glass will have a natural vibration, will have a natural frequency. When the wave, that external sound wave, hits this particular glass at the natural frequency of that particular glass, then what happens? Both of these waves will interfere and they will start to oscillate with maximum amplitude, or simply both of them will be in resonance. So resonance just means that when the external force applied or vibrations produced, or the external wave that is coming and meeting the natural object, when it matches with the natural frequency of that particular object, then both of these objects will start to vibrate at the same rate or at the maximum amplitude. So when this vibration happens for this particular glass, when the wave comes, sound wave comes, both of them will oscillate with maximum amplitude. The molecules are oscillating with maximum amplitude. When that happens, the glass, the structure of that glass cannot withstand that particular oscillation, so it breaks. Same goes for the bridge. When the soldiers stepped on the bridge, vibrations were produced. These vibrations matched the natural frequency of the brick, hence the brick also started to vibrate. The structural integrity of that bridge was destroyed and the bridge entirely collapsed. So that is what a resonance actually means. Now we have to write an equation for that and find out what is the resonance or resonant frequency of the series LCR circuit. So we actually know that impedance, that is the opposition offered in a series LCR circuit, is given by the equation Z is equal to root of R square plus chi C minus chi L whole square, right? So this will give the impedance or opposition offered in a series LCR circuit. For a series LCR circuit to have resonance condition, that is, for resonance to happen, there is a particular condition. So that particular condition is that this particular chi C should be equal to chi L. That is, the opposition offered by an inductive circuit should be equal to the opposition offered by the capacitive circuit. So the opposition of inductor and capacitor should be equal to each other. When this happens, then we say that resonant condition is attained. I have actually explained it in detail in the class. I hope you all remember that. But again, this particular condition is applied, then we can see that Z is equal to, or impedance is equal to, root of R square plus 0, or simply root of R square. So we can also say that under resonant condition, this particular LCR circuit will behave like a purely inductive circuit because this particular resistances cancel each other out. Impedance will be equal to root of R square, or simply R, which means now this particular circuit is behaving like a purely resistive circuit. Automatically we can say that then the series LCR circuit has attained resonant condition. Now resonance will happen. Now we can also find the condition, that is, and under what condition, under what frequency does resonance condition happen. So this is the physical aspect, that is, when the circuit behaves like a purely resistive circuit, or when chi C is equal to chi L, resonance will happen, and this is the resonance condition. So the actual mathematical equation for this can be written down as, that is, chi C is equal to chi L, or simply, so 1 by C omega will be equal to L omega, or simply rearranging, I can say that 1 by CL is equal to omega square. So 1 by CL will be equal to omega square. So we can say that 1 by CL or 1 by LC, however you want to write it, will be equal to omega square, or simply omega will be equal to 1 by root of LC. So this particular condition is the condition under which resonance will happen, or this is the resonance condition. When omega is equal to 1 by root of LC, we can say that it is resonance condition. But again, this is not in terms of frequency. This is in terms of angular frequency. So we can say that we can express this in terms of frequency, linear frequency. Why I am doing that is because sometimes problems in the examination will come in the numerical form and they will give you linear frequency. So linear frequency f is equal to or mu is equal to. So to attend that particular questions, we need to make this angular thing into linear sense. It's very simple. We already know that omega is equal to 2 pi mu or 2 pi by t. So then we can apply this here. So we can write this particular equation as 2 pi mu is equal to 1 by root of LC, or simply I can rewrite this as frequency mu is equal to 1 by 2 pi root of LC. So this is the resonant condition. To find out resonance frequency, you can use this particular equation, that is mu is equal to 1 by 2 pi root of LC, and that is all about resonance. So I hope you have all understood about what is resonance, what is the average power in that particular circuit, and the little things that come with that. So one more thing is that we have to study about power factor, and after that the last topic is transformers. If you have studied both of that, this entire chapter will be over. So I'll come again with a new topic, that is power factor. Until then, I hope you have understood everything. Thank you.